There's this invisible force that's basically running the whole show, from an apple falling off a tree to the way entire galaxies dance around each other. So today, in this explainer, we're going to pull back the curtain on that fundamental rule of the universe.
So our story really kicks off with this question. It seems pretty simple, right? But this is the one that supposedly hit Isaac Newton and triggered one of the biggest aha moments in all of human history. I mean, on the surface, they're completely different things. An apple falls straight down, plomp. The moon just kind of hangs up there, going in circles forever. But this was Newton's genius. He realized they weren't different at all. He connected the dots and saw that the exact same force yanking that apple to the ground was also the one holding the moon in its orbit. The Earth was pulling on both of them.
Okay, to really get the moon's orbit, think about whirling a stone on a string around your head. That string is constantly pulling the stone inward, right? That's what we call centripetal force. Well, for the moon, Earth's gravity is that invisible string. It's constantly tugging, constantly pulling the moon towards us, which is the only thing that stops it from just flying off in a straight line into deep space.
And this is where it gets a little weird. You've heard Newton's third law. For every action, there's an equal and opposite reaction. So get this. Yes, the apple is actually pulling the Earth up towards it. So why don't we feel the entire planet lurch up every time an apple falls? Well, it's because the Earth is just so unbelievably massive. The apple's pull is like a tiny gnat trying to move a battleship. The force is there, but the effect is so small it's basically zero.
So this whole chain of logic, from the apple to the moon to the Earth, it led Newton to this absolutely incredible conclusion. This force, it wasn't just about our planet. No, he had stumbled onto a secret rule of the entire universe, a property that connects every single thing to every other single thing. And that's it. That's the universal law of gravitation. Just a single, elegant sentence that applies to everything, everywhere. I mean, think about it. Right now, there is a gravitational force between you and the screen you're looking at. It's the very same force that dictates how galaxies collide billions of light years away. It's truly universal. And of course, in science, this incredible idea gets distilled into a beautifully simple mathematical formula. Now, I know it might look a little intimidating at first, but trust me, every single part of this equation tells a really clear story about how gravity works. So let's dive in. All right, let's just decode this thing real quick. F is the force. That's what we're trying to figure out. The force gets bigger if the masses of the objects, that's m and m, get bigger. Makes sense, right? More stuff means more gravity. But the force gets weaker as the distance between them, d, gets bigger. And that g at the beginning, that's the secret sauce. It's a special number, a constant, that just makes the whole recipe work perfectly. Now, that little squared symbol on the distance, on the d, that is so important. This is what we call an inverse square law. And it basically means that gravity's strength fades out really, really fast with distance. So if you double your distance from something, the gravity doesn't just get cut in half. No, it drops all the way down to 1/4 of what it was. It weakens dramatically. And this right here, this is the value of g. And yeah, that is a ridiculously tiny number. And that's the whole reason you don't feel the gravitational pull from the person sitting next to you or your desk or a car driving by. The force is definitely there, but because g is so small and those objects have so little mass compared to, say, a planet, the force is just way too weak for us to ever notice. You need something planet-sized to really feel it. Okay, so that's the big, grand, universal picture. Now let's zoom all the way back in and bring it right back down to Earth and see how this law plays out in something we see all the time, an object just falling. So when you hear a physicist talk about free fall, they're actually talking about a perfect, ideal situation where gravity is the only force at play. Of course, here on Earth, we've always got air getting in the way, air resistance. But if you could drop something in a total vacuum, you'd see free fall in its purest form, just a constant, steady acceleration from the Earth's pull. And this specific acceleration due to Earth's gravity, it's so important we give it its own little nickname, g. Near the Earth's surface, its value is a constant 9.8 meters per second squared. Now, what that actually means is for every single second an object is falling, its speed increases by another 9.8 meters per second. So after 1 second, it's at 9.8, after 2 seconds, it's at 19.6, and on and on. And this brings us to a classic brain teaser.
We all know a rock falls faster than a piece of paper, right? So we just assume heavier things fall faster. But that's just an illusion created by air resistance. The paper's huge surface area basically turns it into a little parachute. If you did the same experiment in a vacuum where there's no air, a feather and a bowling ball would accelerate at the exact same rate and hit the ground at the exact same time.
And what's really cool is that because this acceleration, g, is so constant and predictable right here near Earth's surface, we can use these really reliable equations of motion. These are the tools that let us predict pretty much anything about a falling object. If you know how long it's been falling, boom, you can find its speed. If you know how fast it's going, you can figure out the height it was dropped from. They make it all perfectly predictable.
So, okay, we get it. It explains falling apples, and it helps us bust old myths. But why does this one law really truly matter? I mean, what does it actually do? And the answer is, well, pretty much everything. Gravity isn't just some abstract idea in a textbook. It is the invisible architect of our entire world. It's the force that's literally holding you on the planet right now. It's the cosmic tether that keeps the moon from flying away. It's the clockwork that guides all the planets around the sun. And it's even the power that pulls our oceans back and forth, creating the tides. It's the ultimate cosmic glue. So I'll leave you with one final little puzzle to chew on, using everything we've just talked about. We know the moon pulls on the Earth. That's what makes the tides. But if that's true, why doesn't the Earth get pulled towards the moon? The answer is hidden right there inside Newton's own laws. Think about mass, force, and acceleration.